for AT&T or something.
Yeah. Didn't that guy, he did the ad for the Can You Hear Me Now, dude? And then he went from one telecom company commercial to another telecom company doing the exact same shtick. Can you hear me now? I can hear you now, or whatever.
I mean, if you're
Anyway,
good at something, like, make a
yeah.
living off it, I guess. How you doing this week?
I'm doing good. How you doing?
I have no complaints. I am busy, but busy doing lots of fun things. So,
Like science stuff,
like,
because you're a nerd.
mostly science stuff.
Yes.
uh, it's definitely something that I I see as a necessary evil, like all the admin stuff that I have to do around traveling and getting to visit awesome places and, getting to see folks like yourself. Ah. Ah, my gosh. Yes. For all of our listeners joining us, welcome to another fantastical episode of Science Actually Presents The Nerd and the Scientist. We are both nerds. Some of us are scientists.
It's like a Venn diagram of geek.
I am I am shocked at the lack of Venn diagrams in scientific papers. Growing up in school, I thought they would be more prevalent, and I have seen
Really?
exactly one Venn diagram in a scientific paper, and that happens to be a paper that I am a co-author on.
Well, you got to bring it back.
Serious. That's cool. It's cool. I think one of the difficult ways, one of the difficult things that Venn diagrams can sometimes be useful for is in science. You're kind of like, I have found this result, and to me, as a scientist in my niche corner of the world, um, I get it. I see why this result is cool. But for other people in the field, and for certainly people outside of science, we need to work on like visualizations, like what's an effective way of showing this result. And these days, we're not only looking at how we can show these results, but also how we can use other senses like sound to display this result. Um,
Yes.
and one of my favorite things is this really, really cool graphic with sound that I think was produced by NASA, where it has kind of a map of the galaxy, like with the plane of the Milky Way in the middle. And it's showing all of the detections of exoplanets,
Nice.
and they show up as different colored dots depending on which telescope found them. Um, and there's actually a audio cue that goes with each and every one of those, and so you can kind of like hear the music of the discoveries, and you can hear the tempo increase as more exoplanet finding missions get launched. So
Mm.
it's a bit more bit more complicated than a Venn diagram, but I think it's really cool. It's amazing how many exoplanets we found.
More than one.
Not that that is correct.
Yeah. I don't know if anyone's guessed yet, but this episode we're talking about Venn diagrams.
Woo woo woo.
Nah, we're talking about exoplanets, and these are planets that are basically outside of our solar system. That's all you
Yes,
have to be to qualify to become an exoplanet. And
that's
do you
it.
know, Kavi, when the first official exoplanet was discovered?
I I do, but I can't remember the exact year. I feel like it was 1993.
Close.
Ooh,
1992.
I was gonna say that.
Yeah, but you didn't. But you didn't.
I failed you. I should just quit right now.
Nah. First, exoplanet was discovered orbiting a pulsar in
Hmm.
1992. Pulsar PSR B1257. The name just rolls off the tongue.
It's just melodious.
Right. It was the first pulse. It was the first exoplanet we discovered, and I think my favorite part of this discovery is that we discovered two. It was one that we discovered two the first time around, and since we didn't have any other previous exoplanets at the time, they were actually given names. Nowadays, there's just star name B, star name C, star name D, because there's just too many. But these two were named Poltergeist and Phobator. I don't know if I said
Oh,
that right, and I don't care. Poltergeist and Phobator.
Phobator.
Yes. And that was back
Interesting.
in 1992. So this is relatively somewhat newish field as far as astronomy goes. It's been going for 30 some years.
Hmm.
And
Yeah.
we have discovered a lot more since.
How many more have we discovered?
Something like in the order of like 52, 5,300, something like this.
Yeah,
So we're
that's depending on when you last refreshed your page.
pretty
Um,
much, yes. It's they're which would make Kavi's data visualization, the music of the discovery of exoplanets,
yeah,
quite quite exciting because that would be 5,000 plus notes.
it's incredible. Yeah, I think it's like over 5,500 at this point. The bulk of which were
Hmm.
discovered by the Kepler mission, um, and it's just it's crazy to me how this was a telescope that had a very short mission. Generally, space missions kind of have an expected life, but really they have enough fuel to last them twice or three times as long. And
Hmm.
so you get to do lots of science with them for many years, even in some cases decades beyond what how long they were meant to survive. Kepler um, had a less fortunate fate in that there was a technical issue that resulted in it kind of living around the duration that was meant to, or maybe even a little bit less. But then they adapted it from Kepler into the K2 mission, where
Hmm.
basically it's like, okay, we can't really move it properly, but we can slightly tilt it and it can face this direction. And so there's a whole bunch of exoplanets discovered in one direction, one corner of our galaxy. So despite everything that happened to Kepler, nearly 3,000
Hmm.
planets
So,
that have been
so
confirmed, and
far,
another 2,000 that haven't been confirmed, but um, are potential planets.
right. That was something I loved about when I was reading about all the different exoplanet missions. Kepler has discovered 2,600 over that around the time that we started, around today's date, actually, depending when you refresh your browser. But the beauty of it is that even though Kepler was decommissioned 6 years ago, it during its time it returned so much data
Hmm.
that researchers are still going through it and they're still finding exoplanets and will have work to do for many years to come before they've combed through it all. It's dizzying how much information that Kepler sent back. So even though a bit short lived, it did a wallop of work.
An absolute wallop. Yeah,
Wallop.
wallop. And I think that one of the interesting things that has come up a lot in we're preparing a decadal plan. It's something that happens in Australia, also in the US, um, maybe elsewhere as well. I don't know. I would assume so. But a decadal plan in astronomy is kind of what are the things that we have done until now? What have they taught us about what we're going to need for the upcoming decade? And it's the sort of thing that we can submit to government funding bodies in order to get funding for different projects to kind of show this is all the cool science we've done. This is what we're going to keep doing. And one of the things, as we're preparing this document now, one of the big important working groups is the group about data, and especially data storage and data archiving, because not only can we barely keep up with the influx of data that's coming in, but also there is so much cool science that has yet to be done with all of this older stuff. And we're discovering now so many new phenomena that, kind of require us have the ability to look back through old data to see things in space that change over years or decades, right? Because if you have this weird pulsation that's happening once every 5 years, you'll only know that if you can look back over the last 50 years of data at this
Right.
point. So it's an incredibly important thing for us to figure out how to do effectively. How do we store this data? How do we retrieve data from archives dating back that far? But that's going to continue to be a problem that we need to figure out with more of these space missions doing incredible, incredible work getting data from space to Earth.
A lot. The same thing is happening with another exoplanet hunting space telescope, Spitzer, which lasted just 2 years longer, or it didn't last 2 years longer, but it ended 2 years after Kepler ended
Hmm.
in 2020. And thanks to Spitzer, it also sent us so much exoplanet data that researchers are still on that project, are still going through and finding more and more uh, 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 exoplanets to look at.
The other interesting thing is that you're targeting exoplanets, but there's other stuff in the field of
Oh yeah,
view of these telescopes. And
oh
one
yeah.
of the fun things for me, because I study transients, which are these time variable changing things. Um, and so I'll find a transient in the radio telescope data that I mostly work with, but then I go to these data archives and I'm like, hang on, did Spitzer look at this? Did Kepler look at this? Did TESS look at this? Did any of these other telescopes look at this area? What else can I get from this data set? Did it happen to observe the weird, wacky star that I'm looking at?
Wow, that's awesome.
Yeah.
That's I, so. Is it? How do I phrase this? So, are there like sections of TESS or sections of Kepler or sections of Spitzer data that you could have possibly been the very first person reading? It's just been sitting there in storage, just waiting for somebody to need it for whatever research they're doing.
I don't know about being the first to
Because that
use.
would be cool.
That would be cool. I think generally generally what we've started doing in astronomy as a field, and if there's an astronomer listening to this and they disagree, please write in and tell me why I'm wrong. I would love to know, and then also feel free to come on as a guest and explain why I'm wrong.
Yeah, please.
Publicly shame me, bring it on. Um, but but generally speaking, um, astronomical surveys, so whether that's a ground-based telescope or a space-based telescope that's kind of like studying a large area of the sky, there'll be a pipeline or a number of pipelines that are designed to ingest the data. So to take it in, um, you'll calibrate it, you'll make it sure that everything is like science ready, and then you'll have a science pipeline that's running through it and looking for specific things. Right? You're not manually going through each image saying, "Oh, there's something interesting here. There's something interesting here." It's all kind of automated, and the automation is only going to look for the things that it's been told to look for, right? So more and more, we're needing to use machine learning tools and algorithms to recognize the signatures or the behavior that would show up in a particular telescope for different types of objects, and not just exoplanets. Um, but it's hard to do that, and so what might be the case is no, okay, so maybe I'm not the first person to look at it, but maybe I'm the first person to manually inspect an image from a particular telescope and look at one object that nobody has studied before, because of the approach that people had to it. You also, like, when you're searching for something, you can search for images, at a particular wavelength or taken on a particular day. In some cases, you won't necessarily be able to like find something on the day you're looking for, but let's say that I have radio observations that have happened over the past year. and at one point in, I don't know, January, there was a burst of radio light. So I could see if there happened to be a burst sometime around January in these other telescopes.
Oh, sweet.
But
I'm going to
it
ask for a
depends.
series of images taken on my birthday.
You could definitely find that sort of thing, but it depends on how lucky you get as to whether or not the telescope happened to be observing that patch of sky at that time.
Got it. That's a lot of observing.
It's a lot of observing. Oh
Oh,
god.
what other missions have been going? The technology that we have up there just keeps getting better and better and better. And one thing that I love that I've learned is that even though Kepler has the record for the most exoplanets thus yet found, TESS is gonna give it a go. One thing specifically, TESS can see further away than Kepler can, and TESS is designed to survey 85% of the night sky, or the sky, which is an area about 400 times larger than what Kepler is able to see. And on top of that, it's going to start. It has the ability to understand the masses, sizes, densities, and atmospheric composition in some cases of some of the exoplanets that it finds.
I
How
think it's yeah.
spectroscopy is a huge thing, and we should do an episode on that alone. But how how can TESS? Uh, TESS, by the way, is the acronym for Transiting Exoplanet Survey Satellite. You don't want me to pronounce how I misspelled it in my notes. Uh, but how can TESS survey so much more and with so much more detail than Kepler, aside from the fact that the technology is vastly different?
I think so. One of the cool things about TESS is kind of this. The problem that Kepler had that I mentioned earlier was the fact that it. I don't know whether to call it like a rotation axis, but like there was a mechanical failure that meant that it was limited into where it could point. Um, Yeah. Whereas, so Tess, on the other hand, kind of is able to do. Um, I think every 28 days, it's able to basically scan like an entire slice of the sky.
Uh-huh.
Um, if you imagine like an orange that's been cut into segments, right? So the peel of an individual segment, if imagine that as like a segment on the
Strip.
sky, a strip on the sky, exactly. And so if the whole sky is a sphere, looking outwards, so it's kind of like Tess can basically cover those segments entirely, and then every 28 days it just does the downlink back to Earth, and so you're getting like more frequent coverage of a wider area. Um, and also, as you said, the technology has gotten better. I have friends who work on the data pipelines for tests, and it's pretty impressive. The amount of information that we're able to get out of just this tiny little hunk of junk flying in space.
Like a junk that's seeing into the freaking past. That's awesome.
It's incredible, and that's why it's been able to. I think I don't know about confirmed number, but like the number of candidates I think is around the 7,000 mark for exoplanets. I think, yeah, I think it's somewhere around that. But there are
Wow.
another 4,000 candidates from tests that are yet to be confirmed. It's as again, it was like a mission that was planned for 2 years and it's been running for 6 years and it's still going.
There you go.
Yeah,
I mean, Hubble's still up there. Hubble still works. And
Hubble
it's
still
been
works.
working for like 34 years, 30 something years.
Well,
It's,
now that they've fixed it.
yeah, but it's incredible. It's just going and going and going and going. It even has taken a few of the earliest profiles of exoplanets before we started
Yeah.
setting up much newer technology. So Hubble, for all its dents and scratches, it's still just chugging along, taking pictures of everything.
Love it. I love it. I have a quick ad for us, actually, that's kind of
Good.
related.
And then when we come back, we could talk about the different methods that different scientists and missions are using to detect
Definitely.
exoplanets.
Definitely. Well, Benjamin, are you tired of tiny telescopes?
Exhausted.
Exhausted. Are you ready for a cosmic upgrade?
I've been.
Well, then you should meet the ultimate space-based telescope.
What?
See galaxies like never before from your backyard. No clouds, no light pollution, just pure, unadulterated cosmos.
Yes.
Order now, and you get a free astronaut ice cream. Call 1-800-STARGAZE. That's 1-800-STARGAZE for the ultimate space-based telescope, because Earth is so last century. Batteries not included. May cause spontaneous star parties.
Oh, I love spontaneous star parties, especially when there's ice cream involved.
Who
Nicely
would be
done.
afraid of that?
1-800-STARGAZER. I hope that works. Anybody calling that number and not impressed with the results, again, another excuse to please contact us.
Please contact us. Tell us who you found on the other end of that phone number.
Maybe that's what we should do. Just start making bogus commercials. Just let people call and complain. We want to hear from you, all positive possible, but we'll take negative comments on
We'll
our
take negative.
commercials. That's cool.
We're also continuing to look for sponsors for our ad segments. If you're interested in getting us to do silly or serious, but preferably silly ads for your company, drop us an email and we can chat about how we can integrate some
Please. We
of
have
these ads
1,500 listeners that would love to hear it. That's a lot.
all around the globe except Antarctica.
Except the bottom.
Except, yes. But yeah, Benjamin, you said you wanted to talk more about the different methods that these fantastic telescopes, the real ones, are using to find exoplanets.
Absolutely. Um, excuse me. Uh,
You're
Going
excused.
back to the very first exoplanets that we found, that we mentioned at the top of the episode, Poltergeist and Phobator, they were discovered uh, via radial velocity.
Yes.
Basically, uh, observers noticed that the star wasn't just sitting there in their view, it was wobbling a bit because something was tugging at it. And the wobble is basically detected by the, correct me if I'm wrong, the Doppler effect. The
Hmm.
light from the star turns a little bit bluer when it moves towards the observer, a little bit redder when it moves away from the observer. And
Yeah.
by detecting the extent of this color change and how fast the change is happening, you're able to detect or understand the 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 the, the object orbiting it. I couldn't get
Yeah.
exoplanet out of
The
my
thing that's
mouth.
doing the
The
thing.
thing, the Death Star. You couldn't detect the exoplanet going around the star, and that's what helps you find it. And
Yeah, that's exactly it.
about
And it's,
1,090 exoplanets so far have been discovered in this way.
yeah. It's it might sound a bit complicated, but yeah, just like you were saying, Benjamin, the Doppler effect, right? So if there's an ambulance or something with a siren that's coming towards you, you'll hear that sound wave compressed, so it'll sound higher pitched, and when that siren is moving away from you, you'll hear that siren, that sound wave. Kind of elongated with a longer wavelength, and so it'll sound lower pitch and maybe a bit slower. So you see the same thing happen with light. So light waves that are emitted from a thing that's moving towards you, the light wave is compressed, and shorter wavelengths become a little bit more bluer. And as it's moving away from you, the light waves become elongated, and longer wavelengths are a bit redder. So we talk about redshift and blue shift. Either way, you're exactly right. The kind of radial velocity, meaning the velocity or the speed of an object in a radial direction. So if you picture a circle and the radius out from the circle, so Earth, if you take to be the center of that circle, and any star being some, distance, some radius away from us. So the velocity in that radial direction basically will be slightly altered. If you take, a couple of measurements, we know what the red and blue shift should be. And what we will see is that there is a slight change, a slight tug in the Doppler effect, as you said, if there is something else there that's pulling the star in some sort of way.
Nice.
Yeah. It's very science. Much science, do the thing.
Much science. Another method in which we are able to detect is uh, transits.
Yes.
And this is the Mamma Jamma. More exoplanets are discovered this way than any other way.
Mm-hmm.
Um, the very first time we did it was in 1999, and we noticed that exoplanet was passing in front of their host star. If you drew a line from the observer, us, and the star far, far away, a planet, when it going around the star, went in between our eyesight, between
Mm-hmm.
us and the planet, and it caused the planet to have a dip in its brightness. It dimmed a little bit and re-brightened back up to its normal, brightness. And
Yep.
this actually can repeat every time an exoplanet goes around its star. The same dip in brightness should happen.
Yeah. It's
And
kind of like an eclipse in a way, but
yes, how can we detect something so incredibly small? I mean, a star is titanically huge compared to its planets.
mm-hmm.
How can you tell if, Earth was in front of it? I'm standing on another star and I'm looking at the sun, and then Earth
Mm-hmm.
happens to go by. How the hell can I tell? It's so
So
insignificantly small.
one way is you firstly have to get lucky in terms of your your sight line or your line of sight has to line up with the orbital plane, right? Because the planets in a solar system, in any star system, will tend to orbit around the star, kind of in one plane, which is because of, it's the same. Planets, according to the nebula hypothesis of how planetary systems form, are basically the leftover material from the formation of the star. So the star is spinning, in one direction, and all the material that's left over from the formation continues to spin in that direction, and that material settles into that plane that flattens out, and that's where all the planets form. So if that plane, that orbital plane, is not lined up with the direction that we're looking at, it gets much harder to find. But the thing is that the further out a planet is from its host star, the more of the light it's able to block, right? So if the moon was much further away from the sun, or sorry, I should say, if the moon was much closer to the sun and further away from us, we wouldn't see total solar eclipses, right? Because the moon would block out less of the light from the sun. So if we're looking at a distant star and we can see these tiny, tiny dips in the light coming from the star with our telescopes, which again, it's another reason to have newer telescopes with improved sensitivity that can get better measurements. Um, if there is a planet, especially if it's a little bit further away from that host star, it'll cover more of the light, and that's how we will see those little dips down in the total brightness. Also, when you see those signals periodically, as you said, doing long observations like Tess is doing, like Kepler did, of the stars, you can pick up on these patterns, even if they're only very subtle dips.
How hard is it then, or how is it? How are you guys able? You guys, you science, space nerd,
You,
man, person,
you
are
people.
you able to tell then by using transits that it's just one or four
Mm.
exoplanets going around? Is there like a wobble in the brightness that you have to just pay closer attention to?
Well, if there are multiple planets, they would orbit if there are multiple planets, they're going to be at different distances from the star, right?
Right.
So that would mean that they would take different amounts of time to go around the star. And so the dips would come at different times. So if you observe it for long enough, you'll be able to see dips that occur with different frequencies or dips occurring at different periods. And those would each set of dips with a particular period or frequency would correspond to a particular
Oh,
planet. Yeah.
nice. Dips. I
Dips,
like.
dips, dips, dips.
Next,
Next.
direct imaging. That means taking a photo of the exoplanet itself, a direct photo of the exoplanet. This is very rare compared to
It's tough.
detecting via radial velocity or via transit. And supposedly, from my understanding, less than 100 exoplanets have been found in this way. Why so few?
Well, planets planets don't give off their own light at most wavelengths, right?
Right.
So when we are looking at other planets in our solar system from Earth, we see the light that they're reflecting from the sun. Um, but basically, if you want to find a planet in a distant solar system, in a different star system, you have to come up with kind of complicated ways of identifying what's the planet and what's not. So one of the ways that people do this is that they use a coronagraph where you basically block out the light coming from the central star and see if after you do that in the image you can still make out a faint planet orbiting around that star, right? Um, because otherwise, just like the center of your image would be so super bright and all the pixels would be saturated. But that's quite difficult, and it also means that you can only see planets at certain distances. So uh, it's kind of tough. There are a lot of interesting projects that are being done, some here at the University of Sydney, like the Ptolemy project, which actually there's a sign for Ptolemy behind me, um, conveniently. And so Ptolemy is looking at other methods of direct imaging that could use um, more fancy, let's say, ways of manipulating the light that's coming into the telescope in order to kind of artificially remove the star and then allow us to more easily detect exoplanets.
Huh. Okay.
Yeah.
I always think that the glare of the star would just wash it all out, but if you're able to, you know, uh, I lost words today. If you're able to take it out artificially after you're taking the image, and you're still have able to detect the little bits of light left over from the planets, I think that's insanity.
It
They were
is,
talking about
man.
fractions of a degree of luminosity compared to a star, and you're able still to detect it, even after just saying, "Okay, take out the star."
Take out the Death Star. Yes. Um, it's really it's not something that I work on directly a lot because I mostly do radio telescope observations. But yeah, some of this optical and infrared stuff is incredibly fascinating. Um,
Oh.
yeah, it's cool. I love exoplanets.
Two more ways to discover or observe an exoplanet. Next one is a very tricky one, and it requires on the chance alignment of two stars from the point of view of an observer. It's called microlensing.
Ah, yes.
How is that?
How does it
I,
work? What do?
it basically it's relying on the gravity of one star to warp the image of something that's behind it, and then the gravity of the next star closer to you to kind of rebend it back so you can see it. And it only happens once. It doesn't repeat because once that alignment is moved on, the two stars have gone their different ways. That's it.
Yeah. Um,
How? How lucky do you have to be to get to see this? This has got to be like winning the lottery.
I mean, yeah, you're right. Like you gave a good description of how it works. It's something that I think there's been maybe a couple hundred planets that have been detected this way previously, but there's a new telescope that's coming up, the Nancy Roman telescope, and we are expecting there to be much more of these microlensing events that are detected with the Roman telescope. Um, yeah, it's. I think it's so cool the fact that like originally when people were thinking about the implications of general relativity, um, and how space time is this thing that can be bent, right? Um, People didn't really believe it, and now we're continuing to see more and more ways that the effects of general relativity, the curvature of space time as a result of a nearby mass, we're seeing it in effect, and it's not just with supermassive objects like black holes and galaxies, but like also stars and planets cause these, as you said, these micro lensing events and cause slight deviations and bends in the way that light travels, right? Because light travels in a straight line, but if the space it's moving through is bent, it will appear to curve.
That's awesome. I'm also very
Yeah.
proud of myself that I actually have the Nancy Grace Roman Space Telescope in my notes.
Amazing.
It's going to be a ground based telescope, not out in space. And it's going to have a field of view 100 times bigger than that of Hubble, which is just incredible. Incredibly. I'm so proud of myself. Yay! One more. This one is cool, and I can't explain it. So you're going to explain it. Astrometry. Basically, the tracking of the motion of a star as it kind of dances across your field of view.
The tracking of a star. Yeah. I I think that the coolest thing about astrometry is the fact that we're getting better and better at identifying billions of stars in the galaxy with space-based telescopes, um, like the Gaia telescope. Um, and I think that the Roman telescope is also going to be a space-based telescope. Um,
Really?
the whole
My notes are
yeah,
not that good then.
checks notes.
I'm
But
check.
yeah, with Gaia, Gaia has observed the entire night sky. It's a space-based telescope, so it's observing the whole sky, and it's done it multiple times, and it's detected billions of stars. And what it's able to do by having multiple detections of these stars is it can identify, and I think we mentioned this in a previous episode. Um, it can do what you might call like a six-dimensional coordinate for each of these stars. So it's telling you its coordinates in three spatial dimensions, and it's also telling you its velocity in three spatial dimensions. So how fast it's going in each of the cardinal directions, if you will. Um, and the awesome thing about this is that we are able to say not only where the stars are to a high degree of precision, but also where they're going. And so when you can do that, you can identify subtle changes in the positions that are caused by other objects there. So the astrometry generally refers to tracking the position with a high degree of certainty of stars. Um, yeah, it's it's the sort of thing that people need to be aware of. People in astronomy need to be aware of in order to make sure that they're not seeing something that um, they meaning that they're not mixing up two different objects that they're detecting. I think like it's kind of difficult to use astrometry to detect exoplanets. So I don't think there've been that many that have actually successfully been found. Maybe like a handful. Um, but you basically need to have like super super duper high resolution um, observations in order to know like with crazy precision what the location is of the star and also how that location is expected to change over time. And then any small deviations in that would let you know that there's something there that you didn't know that was previously there.
Nice.
Yeah. It's a lot.
It's
It's
a
a lot.
lot. The part that kicks me in the head is that in order for some of these things to work, you need to come across that chance alignment of this, that, and the other. You need to have this high end machine running at that time, observing exactly that event.
Mm-hmm.
And in that situation, then maybe you'll get what you're hoping to get. And it just sounds like such an all these things need to align just for one chance. And yet it's already worked a few times because there's just so much out there that I
It's
guess it just happens.
it's like things that we've discussed in the past regarding maybe the Drake equation, which
Mhm.
we've chatted about in the past, right? About the probability of life existing elsewhere in the universe. But all of these events, when you study physics, both on like the particle level, but also on the astronomical level, you realize that you're dealing with low probabilities of events occurring, but extremely high quantities of stuff, right? So, there are these like crazy effects of quantum tunneling where a particle can pass through an energy barrier that it shouldn't be able to overcome. And it does so with such a low probability. But you have billions and billions and billions of particles attempting to do this, in every star, right? This is basically the fundamental way of how our sun works. And so in order to actually have this uh in like the fact that this works is purely due to the fact that it's a high number thing, right? So you have a low probability thing that's being tested so many damn times.
Ah, space is big.
Space is very big. Yeah,
Space is
that last
huge.
effect I was talking about is called the Gamow effect, Gamow. So yeah, it's like fundamental nuclear fusion. Like things don't work if this doesn't happen, and it shouldn't happen, but it does. So yeah,
Gamow.
Gamow, Gamow, meow 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 meow. Yes,
Gamow.
uh, where if people want to find more information about any of the things that we've spoken about, you can check us out online. You can
On the
ask us
internet.
questions on the interwebs. We are everywhere. Um,
We are. We are
where
everywhere.
can
We are
people find
nowhere.
you? Where can people find you mostly besides everywhere?
Mostly. If you guys want to find me online, it's as easy as one, two, open your browser, type in Facebook, go to the search, type in science actually, and there you'll find us. Find me anyway. Look up science actually.
Mhm.
You can find us primarily on Facebook. We're also on Twitter, Instagram, Hive, Mastodon, Blue Sky, uh, TikTok, YouTube, and LinkedIn. Actually, the TikTok and uh, the YouTube is this wonderful show. If you'd like to watch us talk about the things that you're listening to, go to the YouTubes.
Go to the YouTube. You
And
can see
if
us
you'd
there.
like to see this show in little 8-minute spurts, go to TikTok where you'll find that plus a daily science fact, which is always fun around the water cooler at work. Where can people find you, Kavi?
Well, speaking of daily science facts and fun, you can find me at Fun Fact Science on all of the social media platforms. I'm there. I'm everywhere. Memes, science facts, and trying to share interesting science work that's being done by myself and other people in the field. Um, this has been another incredible, fantastical science adjacent episode. Science actually presents the nerd and the scientist. I'll see you next time.
See you next time. Thanks for joining, everybody.